First, exam 3 is on Monday.
Oh yeah, what day is our final scheduled for?
I can look that up.
The 20th, 8 a.m. to 10.
Oh, it's the Friday, right?
Yeah.
Yes. I also have physics finals that I'm giving on Wednesday and Thursday. So if those work better for you, you can definitely take them then. But yeah, the way it's scheduled, D-Form is at 11, I think, on Friday, and Thermo is at, yeah. Statics is at 11 on Friday, and Thermo is at 2 on Friday, I think.
I have statics at 8 a.m.
Oh, 8 and 11.
And thermals at 11.
Yeah, that's okay.
Calc is the next section after this, and
Yeah.
it's Friday at 11. So
Okay, so yeah, I can be flexible with that.
I mean, if it's 8 to 11, that's fine. Can I sleep in and start later? Yes.
7.
Okay, everybody shut up now. So exam 3 is on Monday. The topics for that are everything up through internal loads. Anybody have any questions about the test or problem questions related to those topics?
Is it going to be more like specifically internal load stuff, or is
No.
it going to be like
Well,
you give us a structure and we just do like the whole thing?
That's one way I can do it. It'll definitely be focused more on, yeah, expect something about structures and something about internal loads, and then probably something from the stuff before that somewhere, you know. Or, I mean, since statics, I guess, is so cumulative by itself, maybe just, yeah, like a structure and a internal loads or something. Yeah. Any other questions about the test? Yeah.
Is the final going to be statics or a mix of everything?
The final?
Yeah.
What else is there besides statics?
Internal loads, everything we've learned.
Oh, you mean the structures?
I think he means friction instead of statics.
Oh, friction.
Oh, okay. Okay, I got you. All right. Okay, yeah. No, the final is going to be a little bit longer than the regular ones, you know. I mean, more like maybe an hour and a half long or something, you know. And so I'll be able to fit in 1 or 2 more questions. There will definitely be at least one friction question, probably just one though. And then the rest is just like a cumulative final, you know. Yeah. Any other questions? Okay. So last time we were working on this problem. I got it here on my telephone, my handheld telephone. So the question was, we had a single threaded screw with a radius of 1 centimeter, 0.01 meters, and a pitch of 4 millimeters, and a coefficient of static friction of 0.1. If the screw supports a weight of 2,000 newtons, so first, what's the couple required to initiate motion up to lift this weight. And we answered that last time, and I think we got 3.29 Newton meters. Yep. And so now we're going to do the same thing. What's the couple required to initiate motion down? Okay, so if you think of this thing, so you're lifting this screw and you have your weight on top of it. You would expect that initiating motion up would be harder and initiating motion down would be easier because gravity is working with you when you're going down and fighting against you when you're going up. So we should see that, okay? And so just always keep that in mind for sort of understanding what's going on. The only difference between these two cases is how weight interacts with stuff. Okay, so we already figured out the angle before. Remember, so if you unfurl this thread, make it like an angled ramp, one time around you have 0.004 there, and you have the circumference 2 pi times the radius as the base. And so we calculated this theta. You just use SOHCAHTOA to find theta. And so it's the inverse tangent of 0.004 over 0.0628. And that gave us 3.64 degrees. And now the free body diagram. We have a weight down of 2,000, straight down. This time we're initiating motion down the ramp. So our Q is going to be this way. Everyone with me on that? The normal force is like this. The friction force is fighting against that Q that's trying to make it move. So this is 0.1 N. Now we have to use a rotation matrix to transform the components of the 2,000 and the Q. The 2,000 is the same as it was before. So the rotation matrix times 0, negative 2,000 is equal to negative 126.98, negative 1995.97. Because we're still using the same coordinate system as we did before, and that weight is still in the same direction it was before. But the Q is in the opposite direction now. So to transform that force Q, we're going to multiply this rotation matrix times, in our original coordinate system, this is in the negative x direction. So we're going to multiply by negative Q0. That's a lot of Q's. And we get negative 0.998 Q, positive 0.063 Q. And this rotation matrix Q is cosine of 3.64, sine of 3.64, negative sine, cosine. Any questions about that transformation? All right, so now we can go to Newton's second law. So we have negative 126.98, negative 1995.97, plus negative 0.998 Q, 0.063 Q, plus 0n. Now this time the friction force is in our positive x direction, so plus 0.1 n 0 is equal to zeros. And so we get two equations. The first one says negative 0.998 Q plus 0.1 N is equal to 126.98. The second one says positive 0.063 Q plus N is equal to 1995.97. Great, that's better. So, okay. So it requires a force to the left of 72.3. And yes, you're exactly right. If you enter it right and you get a negative answer for your Q, it just means that Q is in the opposite direction at the point where motion starts. So it would mean that this thing would naturally spiral down unless you fought it a little bit, you know. But it turns out we didn't get that, so that's good. Any questions about that?
Yeah. So the 0.1 times n, the friction force.
Yeah.
Is that a point force acting on the middle of the object where n is?
Oh, I didn't make this a couple yet. We got to do that. That is okay? So which force?
The friction force. 0.1 times n.
So are we
Yeah.
thinking about this like particle-wise a little bit?
No, we are not. That's a good question because in the next thing we're going to do, we're going to think about it particle-wise. But what we're doing is we're thinking about the entire area of the thread that extends around and around and around, condensed down into a little tight package, you know? Because the way dry friction calculations work is you don't care about that surface area or that contact distance, you know? So we're just drawing it this way basically, but this is what's going on for the entire thread. Okay?
Because were you asking that because like we're not calculating a moment? Is that...
I guess. I don't know.
Well, yeah, I mean, that's the sum of like, so if you took a quarter of that thread or whatever, it would be taking up a quarter of that total force, you know?
Okay.
That's the way this works. This is the entire friction force on the entire thread.
So it's like sort of like a distributed load, but not really.
It's like after you take your distributed load and turn it into a point force.
Yeah, that's kind of what I mean.
Yeah, right.
Okay.
Okay, so the last thing I guess we have to do is we want the couple. We don't want the force pushing on the back of the thread. That's not like a real thing. So 72.3 is equal to m over r. And so m is equal to 72.3 times 0.01. And so you can,
Oh, I know what you did wrong. In
what?
Row echelon form, you did 0.1 n instead of 0.01 n.
No,
Point-
that's supposed to be 0.1 now.
That's the coefficient of friction.
Oh. No.
Yeah, we have a 0.1 and a 0.01.
Sorry.
That's right. So now what do we have here? We got a couple of 7.23 Newton meters, which is bigger than the one we got before, and that's also,
I think that you just need to move it over one more decimal place.
That's point.
oh, God, I'm glad you guys are here.
Right back at ya.
No, I did it again. 0.72 Newton meters. So very little couple to require to get it moving down the ramp, and a bigger couple required to move it up the ramp, to lift the weight. So everything does make sense. Yay. Any questions about that? Okay, so every problem is the same. You know, once you've seen one problem, you've seen them all. So that example can guide you through anything. But remember, you need to get comfortable going through these derivations like this. Okay. So the types of friction that we're doing here is square threaded screws, belt friction, and bearing friction. And there are two types of bearings, journal bearings and thrust bearings. And so now we're done talking about square threaded screws and we're going on to belts. And this is probably the trickiest mathematically. So this is the idea of belt friction. So this is Rapunzel in her tower. And this prince wants to come up to the tower and, you know, says, let down your hair, and she does. And then here's the prince.
I think this is my favorite drawing so far.
It's a little involved. Can't talk right now.
I like the hair. It's just not supported by anything other than
Well, yeah, so that's what I'm getting at here. Okay, so
I would say it's a close tie with the emu.
okay, so does she like this? No. This is not great for her. Okay? Or a great start to their dating life. Okay, but the idea of belt friction is, you know, she has like a pillar outside her window. So instead, now, she's smart. So she takes her hair, wraps it around the pole a bunch of times, And then the prince climbs up. It's a little uglier prince this time, unfortunately, but
Fell down.
yeah, exactly. That's exactly what happened. Okay, so this time,
Lost his hat too.
yeah, well, in the fall, obviously, yeah. All right, so the prince weighs the same in both cases. The tension on this part of the hair is the same in both cases, but the tension on the other side of the hair, after it's wrapped around this support, is much less in this case than in this case. So that's the idea of belt friction, and it doesn't have to be hair. It can be any kind of cable.
Oh, man.
Okay, so imagine a top-down view of the pole, or a view of the pole from above. So there's a cross-section of the pole. We're just going to, for this derivation, I'm not going to consider multiple wraps around. We're just going to consider partly wrapped around, but it actually doesn't matter in the math, so it's just easier to draw, to visualize what's going on. So the cable is wrapped around the pole from this point to this point. And there is, so I guess I'll include a little bit of the cable that's coming off of the support. And so there's a force T1 over here. We'll think of that as the smaller of the two tensions. And there's a tension over here, T2, that's the larger of the two. And so like, that means this is the one supporting the prince. And this is the princess's head. Okay. And this angle between these two we'll call beta. And so what we want is, we want to calculate a ratio T2 to T1 in terms of that angle beta and the coefficient of friction between, this is between the support and the belt. Okay, everyone with me on that? So the way we're going to do this, so I'm glad you guys asked a couple clarifying questions about what we were looking at with the free body diagram last time, because last time with the square threaded screw, our free body was the entire thread of the screw. Okay, but now we're going to go to like a infinitesimal kind of thing. I guess we'll do it as a limit, but we're going to, so our free body is a small piece of the cable in contact with the support. So, there's our free body. And this isn't part of it. I'm just drawing this so you can visualize this angle. The total angle, so this would be the center of the support. The total angle here is delta beta. That's the Prince's fraternity. And so that means that if we split this in half, we have a delta beta over 2 on each side.
It's like pizza.
I know. I thought that as I was making it, like, this is the most delicious kind of friction. And so now let's think about the forces. This is just labeling stuff. But what are the loads acting on this? And let me actually make I'll make this a dotted line. Okay, so over here, we have I'm going to call this a tension T. That's not the T1 or the T2. That's just some intermediate tension at this one little piece. And there is a normal force this way. And the higher tension is on the right side. And so I'm going to call that T plus some increment, delta T. And now this cable would be accelerating on the support if there wasn't a friction force fighting the bigger tension. And so we have a horizontal friction force this way. Make sure that looks horizontal. And this is the coefficient of friction times the normal. And actually, this normal force is also, since we're just looking at a small piece, this is just a piece of a normal force. We're going to do a limiting thing to turn this into differentials. And so this friction is going to be the coefficient times this little piece of the normal force. Everyone with me on that stuff? Okay, and notice that the angle between, like, let's look at just that T, that force coming off labeled T. How far is that from horizontal? Well, it's perpendicular to this red dotted line. And so it's just delta beta over 2 from horizontal. So we're going to use that with sine and cosine to come up with the components of these. So, this is delta beta over 2. And so now I'm going to go to Newton's second law. This is a little bit cluttered, but there are only the 4 forces acting here. Everything else is just making sense out of the geometry. Okay, so if you don't draw those things in, it doesn't look nearly this crazy. So in the horizontal direction, the x direction, well, let's just do it as vectors. So we have negative t times the cosine of delta beta over 2, negative t times sine of delta beta over 2, then on the other side we have positive t plus delta t times the cosine of delta beta over 2. And positive t plus, so for the y component, you can see that's negative. So we have negative t plus delta t times the sine of delta beta over 2. And then the two horizontal forces, plus 0 delta n plus negative mu delta n 0. And now we'll take the limit as delta beta goes to an infinitesimal d beta. So we have one equation that says negative t cosine delta beta over 2 plus t times the cosine of delta beta over 2 plus dt times the cosine of d beta over 2 minus mu dn is equal to 0. And what can we say about this stuff? So this is from the x equation. You can see that no matter, we don't have to do any limiting stuff to see that two of these terms cancel. And now if that d beta is infinitesimal, cosine of this infinitesimal thing we can just replace with 1. Okay? Like as a first order approximation, this is just equal to 1. That's a pretty common simplification when you take limits as things go to, as lengths go to 0 or whatever, as angles go to 0. Okay, so so we have that dt minus coefficient dn is equal to 0, or in other words, dt is equal to mu dn. And now we'll go to the y equation. In this one, nothing cancels. So we have negative t sine of d beta over 2 minus t sine d beta over 2 minus dt times the sine of d beta over 2 plus dn is equal to 0. And so now instead of cosines, we have sines. When you take the limits as the argument of cosine goes to 0, you get 1. What do you get as you take the limit as sine goes to 0? This is another good one to remember. Well, it does go to 0, but before it goes to 0, it goes to the argument. Do you remember that? Like the limit as theta goes to 0 of sine theta is theta in radians. You've seen that before somewhere in Calc 1 or something. And it's really useful in these kind of derivations.
So you're saying that those would go to d beta over 2?
Yeah, that's right.
Times d.
So we have negative t d beta over 2 minus t d beta over 2 minus dt d beta over 2 plus dn is equal to 0. If these are all infinitesimal, this one gets extra infinitesimal. So this goes away because it's much, much smaller than the other terms because we have the two infinitesimals multiplied together. Okay. And so what we get for our final thing here is negative t. These are both dB over 2, so negative t d beta plus dn is equal to 0. And so dn is equal to t d beta. Okay, so we have, these are our two equations. And I want to solve these as a system. So I'm going to plug in what I found for, I'm going to plug double star into star, and we'll get dt is equal to mu t d beta. And now we can integrate both sides. I'm going to pull the t over here. And we're going to integrate over the entire contact. And so we get natural log of t evaluated from t1 to t2 is equal to mu beta from beta 1 to beta 2. And so in other words, natural log of t2 over t1 is equal to mu. This difference in betas is just what we called beta before. This is the entire angle. Well, that's pretty much what we want, but not quite. We want a ratio of T2 over T1. So the thermo people are used to this. We're going to raise each side as a power of E. E to the natural log just gives you T2 over T1. And this is E to the power of mu times beta. And you can use that for a beta that's less than 2 pi, more than 2 pi, whatever. This works all the time. Okay, so good things to remember because these come up in derivations all the time. So first, the limit of cosine of theta as theta goes to 0 is 1. Second, the limit as theta goes to 0 of sine theta is theta. This only works for radians.
These are all in radians, right?
Yeah.
Including our
Yeah, anytime you're using derivatives at all, everything has to be in radians. Yeah. So yes, our final answer has to be in radians. And the third thing is the limit of how do I want to say this? Let's say, let me give two things. Let's say as alpha goes to 0 and beta goes to 0, the limit of I don't know how to say this, alpha beta over just alpha is equal to 0. Seems sort of obvious when you write it this way, but that's why I canceled that term with the two differentials multiplied together. Okay, so this is why I said in this derivation dt d beta over 2 went to 0. Okay, any questions about that? We'll spend more time on that next time. Okay, goodbye.
I have a question.
Yeah.
Towards the beginning when you had t on one side and t plus.
Yeah.
Why was that not just its own separate variable rather than being this t plus?
Well, yeah, just because we know that there's more tension on the cable on this side. That's the print side, and less over here. And we know that they're changing continuously. So this is not going to be just some crazy value, 50 newtons more. It's going to be this plus some just incremental amount.
I suppose the question is, how do we know that it's delta t rather than anything else? How do we know that it's so direct?
How do we know they're related to each other?
For both tension.
Yeah, it's just the same cable, and so we know that it's because this t is a continuous function. That's why, I guess.
So then do we have to do that math every time, or do we just go straight to the derivations?
Yeah, I do want you to do this derivation every time, but so here's sort of like in a way you could kind of challenge me on how much depth is a derivation. I guess I want to see this free body diagram. You don't have to show me any of the geometry or anything, but I want you to show these 4 things, put them in Newton's second law in some way, and derive it. But you could skip some steps, and I'd be happy with that.